you able to see the screen? Is it
Yes,
visible?
sir. A little
Yes,
bit, you
sir.
have to maximize a little bit.
Sure. At x is equal to 0, which is your u naught of x. This we considered the first example. The first example where we considered this to be greater than, all right, okay. So x less than 0. Is it all right? This was the first example that we considered
Yes, sir.
yesterday. Let me call this as example number 1. Example number 1. Okay. All right. So it is clear that now we have understood that how to construct the solution. This is your initial profile, u naught x, right? And for x less than 0, the function is defined, the function value, right? The u naught x is defined to be 1. On the right, it is 0. U is equal to 0. Remember that along the characteristics, what are the characteristics? Dx dt is equal to u. Along these characteristics, u remains constant, right? Which implies, so if this is a typical xi here, this implies that x is equal to your xi plus, this is nothing but u naught of xi. So t times u naught of xi. X is equal, these are, I mean, this constitutes, right, this equation. If we allow xi to vary, we obtain the family, one parameter family of characteristic curves. And along these characteristic curves, the solution is defined. So in fact, this is the analytical form of the solution, right? This is the analytical form of the solution. It helps us to construct the solution. Look here, this is your xt plane. This is your xt plane. At t equal to, yes, for xi less than 0. Look here, the characteristics issuing from this part of the real line, where xi is in R as a matter of fact, right? Xi is a typical value of x. So for xi less than, what is the value of u? U is here on this part, u naught x is 1. On this part of the real line, u naught x is 0. And therefore, the characteristics issuing from this part of the real line will carry this information which is available here, right? What is the information available here? It is dx is equal to 1. So you look here, the characteristics are, I mean, issuing from xi less than 0. Characteristics issuing from xi less than 0. What are these characteristics? From here it follows that x is equal to xi plus u naught is 1. That is, these are the characteristics. The characteristics, so the leading characteristic issuing from here, this is your x is equal to t or t is equal to x. The remaining ones, in fact, they are all parallel. They are all parallel. Is that right? A typical, I mean, this is a typical value xi is somewhere, that is for different values of xi, we get different characteristics. And all these characteristics, they carry this information which is available here on the initial line. All right. What do we notice here on the right side? On the right side, so it's very clear. What is the solution now? Immediately I can form the solution. What is the solution now? Solution is u is equal to u naught of xi, and xi is nothing but your x minus t. Is that right? And we know that u naught xi, in fact, and here it is 1. So u is equal to 1 in this part of the, right? Here u is equal to 1. I mean, all these characteristics, they carry this data, initial data, and therefore u is equal to 1. What happens to the characteristics? Hello? Characteristics issuing from this part of the real line, that is xi greater than 0. What are the characteristics? They are the vertical lines.
X equal to Z.
Right, right. So these are, as a matter of fact, x is equal to z. These are the characteristics. So look here, the breaking takes place immediately right at the origin. These are the characteristics emanating from this part of the real line. Right? So you can see here that here u is equal to 1, here u is equal to 0, because all these characteristics, they carry this information into the region. So resulting solution would be 0. Now this is your multi-valued region. This is your multi-valued region, right? So what we do, we replace this, because the characteristics note that the characteristics issued from the real line t equal to 0 intersect in the region. What is that region? Wave-shaped region. Wave-shaped region. It is bounded by the lines x is equal to 0. This is the line x is equal to 0, and this is the line x is equal to t. And so, which indeed is a multi-valued region. Why I call it multi-valued region? Hello, who will tell me? Why do I call a multi-valued region? Because when the characteristics intersect, this characteristic will take this value 1, this characteristic will take value 0, and at the point of intersection, the solution, I mean the value of u, ceases to be single valued. Is that right? It is multi-valued. So it's a multi-valued region. So what is our methodology? Our methodology is to replace this multi-valued region, this multi-valued region needs to be replaced by a discontinuous curve or discontinuity. Say x is equal to x of t. This is a smooth curve. This is a smooth curve across which u is discontinuous, its derivatives are discontinuous. This is our objective. How is it possible? Hello? How is it possible? How is it possible? How we can replace, how to get this discontinuity? We invoke RH condition, right? We invoke RH condition. So the RH condition implies that dx dt, this is equal to what? F of ul square minus f of ul minus f of ur divided by ul minus ur. And what is L? We assume. You see, this assumption is extremely important because I told you last time that from a given conservation law, I can derive infinite number of conservation laws, right? So it is assumed that the conservation law is this. U square upon 2x, this is equal to 0. This is the conservation law. It is assumed that the evolution of u at later times is governed by this conservation law, right? So if this is the case, then what do we get? Half of ul plus ur, and this is your half of 1 plus 0, that is your half, and this implies that x is equal to t by 2. The constant of integration turns out to be 0 because the discontinuity is very right, supposed to pass through 0, 0. So here the solution would be, now I will write, this is your solution, 0, and this is the discontinuity, x is equal to t by 2, and on the left of this discontinuity, u is equal to 1, on the right of this discontinuity, u equal to 0. This is a weak solution of this initial value problem, is a weak solution, which I can write xt. This is equal to 1 when x is less than t by 2, 0 when x is greater than t by 2. This is Now you can see here, you can verify that this is indeed a weak solution. It satisfies the initial condition, it's very clear, right? At t equal to 0, you can see that u is 1 and 0, it satisfies the initial condition, correct? This solution satisfies the differential equation identically. You can also see that the t derivative, in this domain, in this region, right? The region on the left of this discontinuity, u is constant, which satisfies this differential equation identically. On the right, u is equal to 0. It satisfies this differential equation identically. So in the region, this is the only curve, x is equal to t by 2. And we know that x is equal to t by 2 satisfies our H condition, right? It has been obtained from the conservation law, correct? And therefore, it's a solution. Why do I call it a weak solution? Because it includes a discontinuity as well. The solution is discontinuous across x is equal to t by 2. That's why it is a weak solution, right? It's a weak solution. Your usual method of characteristic fails here. It cannot give us the solution of such a problem, right? We need to make further considerations that how to extend the validity of the solution beyond this breaking. Please take care of Mike, please. All right. Now the other example I considered quickly, but again I review it briefly. This was the differential equation remains the same. What is the name of this differential equation? By the way, it's a well-known equation. What it is called?
Burger's equation.
Burger's equation, very right. Burger's equation. This is your 0, 1 now. On the left, it is 0. On the right, it is 1. Again, what are the characteristics? Dx dt is equal to u. By the way, what does it mean? Characteristic means dx dt. You see, this is the velocity. What does it mean? The velocity of what? Points on the characteristic, right? Dx dt is equal to u. This is the characteristic speed. This is also referred to as characteristic speed. I mean, this is the speed with which the points on the characteristic propagate. Is that right? You see, I use the word propagation, I use the word wave, but actually this is, I told you in the beginning that solutions of hyperbolic equations, they represent wave phenomena, right? Solutions, they represent wave. So either you say that u is a solution of this, or you say that yes, it is a wave solution. I will say that the wave, this is the wave speed as a matter of fact now, right? The characteristics, in fact, they are the moving wavelets, and the behavior of the solution on a characteristic corresponds to the idea that, that information is followed by that characteristic front, right? That is the whole idea. So anyway, so this is to be kept in mind. The dx dt is the characteristic speed, which is your u. And we know that, you see, if c is an increasing function of u, you remember I explained it in the beginning, higher values of u propagate faster than the lower ones, right? Is that okay? If it is an increasing function, so naturally dx dt is equal to u. It's very clear from here that higher values, they propagate faster than the lower value. This is to be kept in mind. These are very important things, you see. Again, I will come back to it. So what are the characteristics? So this is your initial data. This is your initial data. This is your u naught x. This is x. Here on the left, u naught x is 0. On the right, it is 1. U naught x. This is your, right? You see, this is called Riemann problem. Riemann problem. This is called Riemann problem. What Riemann problem says? Riemann problem says that, the two constant states, they are separated by, the two constant states, they are separated by a single discontinuity. So u naught x is one constant state, u naught x is equal to 0 is another constant state. And these two constant states are separated by a single discontinuity located at x is equal to 0. So this is referred to as Riemann problem. So here in all these problems, in fact, we are finding the solution of the Riemann problem. Earlier we considered Cauchy problem, right? Cauchy problem. But here these are the Riemann problems. So now look here, what is the behavior in the xt plane? We can quickly see. This is your xt plane. So these are the characteristics. These are the characteristics which are issued from this part. So instead of writing everything which I did earlier, it's not needed. I will just write down, these are the vertical characteristics, okay? Here we get vertical characteristics. Because the characteristics issuing from this part, they carry this information into the region. Right, xi is an atypical point, and I know that the solution is x is equal to xi plus t times u naught of xi, and u is equal to u naught of xi. Right, xi is a typical point, in fact, a fixed x as a matter of fact, right, for a given characteristic. A given characteristic from passing through a point xt meets the line t equal to 0 at a fixed point, I call it xi. All right, this is the analytical solution. What are the characteristics issuing from here? U naught x is equal to 1. So these are the characteristics. This is the leading one. X is equal to t plus xi. So here x is equal to t. And yes, they are all parallel. This, if suppose this point is xi, it is x is equal to t plus xi. Is that right? So these are the characteristics. Look here, we don't have any information in this gap. So here we know the solution here, all these characteristics, they carry this information into the region. So u is equal to 0 in this region, u is equal to 1 in this region, but really we do not know what is the solution in this gap. We really do not know the solution in the gap, which is a wedge-shaped region bounded by the lines x is equal to 0 and x is equal to t, right? So what to do? Now you see your data, in fact, is not able to control the solution in this gap. As a result, there could be many solutions. Look here, one possibility is this, one possibility. One possibility is same which I did earlier, that I take all the characteristics issuing from 0, right, along these straight lines. These are the straight lines issuing from 0, and they take all the values between 0 and 1, okay? These characteristics issuing from 0, they take all the values between 0 and 1. So since they pass through 0, xi is equal to 0, so x is equal to t times u naught of xi, but xi takes all the values between 0 and 1. Is that right? That's why I retained here xi takes all the values between 0 and 1. So from here, what do we get? Hello? That u naught xi, typically, you see, what is xi? Xi is any x line between 0 and 1. So it's very clear, u naught xi is your x by t. What is u naught xi? U naught xi is u. Therefore, uxt is your x by t. This is the solution in this gap. Hello? Is it, one can see quickly that it satisfies the differential equation identically. It satisfies the differential equation identically because the t derivative, look at the terms on the left, ut will be your minus x upon t square plus u is your x by t and ux is 1 by t. So left hand side is identically satisfied, 0. Is that right? So this satisfies identically, and it is very clear that it satisfies, okay? It satisfies u is equal to x by 2, x by t. It satisfies the differential equation identically. Look here, this is a constant state, this is a constant state. Here u is equal to x by 2, and therefore the solution can be written as 0 when x is less than 0, right? And it is x by t when 0 is less than x is less than t. This is the line x is equal to t. In this region, it is x by t. and in this region it is 1. That is when x is greater than 0. When x is greater than t, then it is 1. So this is the solution at any time t, okay? This is the solution at any time t, and this satisfies the differential equation identically, okay? It satisfies the differential equation identically. You can see it satisfies the initial condition because on x is equal to t, you can see here it is 1. So actually you get this solution 0 and 1. It satisfies, it is completely identically satisfied in this region, in this region, in this region. Yes, what happens along x is equal to t and x is equal to 0? Hello? Obviously, if I approach this line x is equal to t from left, obviously I get the limiting value to be 1, which coincides with the limit with the value u is equal to 1 on the right. It means u is continuous. U is continuous along the boundary. But hello, any query? Any question? Hello?
No, sir.
Okay. So look here, but I call it a weak solution. Why is it a weak solution? Hello? It is a weak solution. Yesterday, in fact, I posed this problem. You think about it, that, okay, can you please, any one of you, how is it a weak solution? Because it is continuous, right, all through. As a matter of fact, here u0, when you approach this line from right, x approaches 0, so u goes to 0, and from left also. So it's a continuous solution. It's a continuous solution. But I call it a weak solution. It is differentiable. It is differentiable in this reason. It is differentiable in this reason. It is differentiable in this reason. Why do I call it a weak solution?
Derivatives are discontinuous.
Very good. Derivatives are discontinuous across these lines. X is equal to 0 and x is equal to t. Look here, what is the x derivative? 1 by t on the left, but on the right it is 1. So the x derivative is discontinuous. Similarly, t derivative is discontinuous. Like this, derivative weak solution because derivatives ux and ut are discontinuous across the lines x is equal to 0 and x is equal to t, okay? So that's why it's a weak solution. So this is one possibility that I get a weak solution of this kind. This is, I will call it U1. U1 is one solution. Now you see there is another possibility. Another possibility, what is that? I can introduce a discontinuity also. Is that right? I can introduce a discontinuity in this region. And what is the discontinuity? So that it satisfies the RH condition. So that it satisfies the RH condition. What is RH condition? RH condition is dx dt is equal to f of ul minus f of ur divided by ul minus ur. And again, this is your ul plus ur, right? Again, you see it has been assumed in the beginning that the evolution is governed by a partial differential equation of this kind. That is the conservation law. That is the conservation law is this for this, because there could be infinite number of conservation laws. I uniquely specified the conservation law, but even then there is a problem. Can you see? This is one solution. The other solution could be, yes, I introduce this discontinuity. This is your x is equal to, this is 0, 1, so half x is equal to t by 2. Again, the discontinuity is there, right? And I construct this solution in such a way so that you see the characteristics emanating from here, they carry this information. Here on the left, it is 0. It is 0. So here, in fact, throughout this, it is 0 because all these characteristics are parallel. All these characteristics are parallel. And here all these characters, here u is equal to 1. Here u is equal to 1. So from these points, I take characteristics emanating from the shock, and here, so u is equal to 1. So here you see the solution at any time t, I call it u2. u2 is your, on the left, it is 0. So 0, this is your, what is the equation of the discontinuity? X is equal to t by 2. So when x is less than t by 2, it is 0. In this region, hello, what happens? In this region, u is equal to 1 when x is greater than t by 2. This is the solution. You can see that on the left of this discontinuity, this is the discontinuity. On the left of this, u is equal to 0, which satisfies the differential equation identically. On the right of this discontinuity, u is equal to 1 in the whole region, u is equal to 1. It satisfies the differential equation identically. You can see that initial condition is satisfied, right? On the left it is 0, on the right it is 1. Okay? And only, you see what remains? This discontinuity, and this discontinuity satisfies our RH condition, right? Which we have derived from the conservation law, and therefore this precisely is another correct solution. Now the thing is this, what to do? I told you yesterday that we have non-uniqueness on 2 counts. Number 1, non-uniqueness of the conservation law. Number 2, non-uniqueness of the solution. So I told you that even if the non-uniqueness of the conservation law, yes, if it is resolved, right, by experimentalists, that yes, this is the correct conservation law. This is fixed, but even then the problem is not resolved. There are, in fact, I can give you n number of examples where there are infinite number of weak solutions. Not only 1 or 2, infinite number of weak solutions. 2 is enough in this case for the sake of illustration because time is very short. So the thing is this, there is no uniqueness. So how to introduce uniqueness into the solution? How to introduce uniqueness into the solution? So this problem was resolved by Professor Peter Lex. Peter Lex, he argued, look here how nicely he argued, please try to understand. This is the criterion that he gave, that f of ul should be greater than dx dt, should be greater than f of ur. This is the criterion, a wonderful criterion, when the flux function is convex. So here you see the flux function, this is your f. This is the density function, u is the density function, and u square upon 2 is the flux function, right? So you can see here what it says. What is f here? Hello? You can see here that this f, what is f here? F is your u square upon 2, is that right?
Yes, sir.
And what is dx dt? Dx dt, in fact, generally, if I take this as f of u, then this is your f dash of u. Is that right? In this particular case, the derivative of f dash turns out to be u, which is precisely the case. Is that right? So in general, this is the speed with which the characteristics propagate. F dash u evaluated just on the left of this discontinuity, right? This is f dash, I'm sorry, this is f dash. F dash, this is the characteristic speed on the left. If the characteristic speed on the left of the discontinuity is greater than the characteristic speed on the right of the discontinuity, then Lex proposed that this is the right way. This is the only solution. And in fact, this condition is referred to as Lex's stability criterion. Lex's stability criterion.
So please scroll up the page.
Sure. Lex's stability criterion. What it says, the characteristic speed on the left of the discontinuity is greater than the characteristic speed on the right of the discontinuity. Rather, the speed of the discontinuity is intermediate between these two values. Is that right? Hello?
Yes, sir.
Okay, so this Lex's condition, now intuitively, its proof is not that difficult, but it will take, at least an hour to explain this. So I'm not going to prove it, but if you pick up any good book, you will find its proof, right?
Yes, sir.
Its proof. Hello? Any question?
No, sir.
No,
Its proof is based on vanishing viscosity method. You see, this is the name of the method. That is, we consider this equation, ut plus ux is equal to nu times uxx. Because what happens, this is the idealization in the limit when nu, I mean a number, this is some number which is very, very small, it's positive. In the limit when this nu goes to 0, we say vanishing viscosity. Why this name has been attributed? Because of simple reason, right? Because in Navier-Stokes equation, right, this plays the role of viscosity, right, is the coefficient of second order derivatives. Anyway, is all right. So we find out the solution of this and take the limit, right, as nu goes to 0. As nu goes to 0, we recover this criterion. So you see, it's a wonderful result. And you have to, but intuitively I can explain to you what he says. He says a discontinuity has to be fitted into this solution only if the characteristics emanating from the left and from right, they intersect. So if you look at this problem, hello, here the characteristics, they intersect. So there is a need to introduce a discontinuity. So according to the, and moreover, you can see that f dash ul, what is f dash ul? F dash ul is dx dt, right? Dx dt. What is dx dt? U. It is nothing but f dash u here. F dash u is nothing but, hello, f dash u is nothing but your u, right? And you can see here it is 1 and here it is 0. So f dash ul is greater than f dash ur. Is it all right? Hello?
Yes, sir.
Yes.
And you can see the speed of the discontinuity x by, right? The discontinuity lies in this region. Correct? And therefore, it is clear that since the discontinuity lies in this region, correct? It lies between f dash ul and f dash ur. So it satisfies the stability criterion. So it is a unique solution. What about this second problem? Second problem, we have got two solutions, u1 and u2. Can you tell me out of these two, which is that satisfying the Lexus stability criterion? Hello? I have two solutions, u1 and u2. Yes, which one satisfies Lexus stability criterion? Hello? Anybody?
Yes, sir. Yes, sir.
So please, can you please ask participants whether anyone
Yes, sir. Yes, sir.
answer this question, that why, which out of these two, u1 and u2, this is one solution, this is another solution. Out of these two, which one satisfies the Lexus stability criterion? Hello?
Yes, sir.
Out of these two solutions, u1 and u2, which is the correct solution? What means,
U2 is the correct solution.
why? What is the reason? What is the reason? No, u2 is not correct solution. Why? Why? It is very clear here, you see, because if you look at the problem, these characteristics, they do not intersect. Here the characteristics are vertical lines, here the characteristics, right, they are inclined towards right, they never intersect. This we did, right? There are two possibilities. Either you take characteristics emanating from 0, right? So they do not intersect, or this is the second possibility. But what Lex says, discontinuity has to be fitted only when the characteristics intersect, as we did in the first problem. In the first problem, these characteristics, they do intersect, because this characteristic originating from here, it has slope 1, this characteristic has slope 0, so definitely they are going to intersect. And if this is the situation, whenever the characteristics intersect, right, the continuity of the solution breaks down, your method of characteristic fails, right? This analysis is valid for that, but you see, we have to look for weak solutions. For weak solutions, in fact, we have seen that there is a question of uniqueness, because although we have extended the notion of solution, but in this extension, in fact, we have lost uniqueness. So in order to get a unique solution of a given initial value problem, Lex proposed that a discontinuity is to be fitted. A discontinuity is to be fitted into the solution only when the characteristics emanating from left and emanating from right, they intersect. So first of all, yes, we should not have done it. Hello? Because the characteristics, they do not intersect, right? This is one possibility. This is another possibility. Here we have introduced a discontinuity, right?
Okay. Yes, sir.
Mathematically, it is correct solution, but it is not, it doesn't satisfy the stability criterion. As a result, the solution ceases to be unique, right? It's not unique. So, and moreover, you can see here, f dash ul is not greater than, here it is 0, here it is 1. So even then it is violated. Even if you introduce a discontinuity, hello?
Yes, sir. Yes, sir.
Even if you introduce a discontinuity, this fails. It says that characteristic speed on the left should be greater than the characteristic. Here it is 0, here it is 1. It is less, and therefore it is violated. So this is not admissible. This is not admissible. So only physically relevant solution. So now you see, one can now have a feeling that why did he say all this? You see, it is very clear if the initial data is like this. Hello?
Yes,
If the initial data is like this, then look here, each point on the profile will, because if you look at the values of u, right, these are the larger values, and as compared to the values on the left, is that right? Here u is equal to 1, here u is equal to 0, is that right? So dx dt is equal to u. This is the characteristic speed, correct? This is the speed with which the points on the profile propagate. So this profile, right, it has, or I would say, either you call it a profile, or you call it a solution, or you call it a wave, because the solution, in fact, it is also of similar nature. So in fact, higher values, they propagate faster. So as a matter of fact, if you look at the profile of the solution, at later time, yes, it will be further, the solution would be somewhat like this. The solution at a later time, here it is 0. But each point will propagate faster, and therefore at a later time the solution will take this form. Is that right? Hello?
Yes.
So actually, if you remember in the beginning, I told you it is an expansion. It is a rarefact. It is a monotonic. Here, what happens? Monotonic increasing function. If you just, had it been like this, I could have taken this to be like this, right? It's a monotonic function. So you can see here, if it is a monotonic increasing function, then there is no discontinuity. You get an expansion wave, and you get, so this is the correct solution. This is the correct solution. And that is the reason you see this condition works. So intuitively, one can have a feeling. Now look here, why we cannot introduce a discontinuity. It is very clear that on the left, yes, this is the case, right? On the left, here u is equal to 0. On the right, u is equal to 1. So obviously, there is no way we cannot introduce a discontinuity, because it will go on like this. Next phase, yes, at later time, solution would be somewhat like this, These points will propagate faster, right? So this part of the profile propagates faster as compared to points on this part of the wave. So no discontinuity, this condition is always satisfied, and therefore this is the unique solution. But in the first case, look here, if it is like this, then what will happen? If you look at the solution at later time, here the wave is taller, or the higher values of u, right? As compared to the right, where the value, here u is 1, here u is 0. On the left, u is 1. On the right, u is 0. So higher values of u will propagate faster. Am I right? Hello? dx dt is u. So these points will propagate faster as compared to these points. So what will happen? At a later time, this is your u is equal to 1. It will propagate right further. X is equal to 0. Whereas this is your E is equal. So what will happen? Some part of this wave, right? Some part of this taller wave will overtake some. Hello?
Yes, sir.
Yes, sir.
Is there any query?
No, sir.
No, sir.
So you can see here a part of this wave overtakes a part of this wave. As a result, the wave breaks. As a result, the wave breaks. In other words, the characteristics, they intersect. And as soon as the characteristics intersect, a discontinuity has to be introduced. And then it satisfies the condition laid down by Lex. So this is the whole idea. Now with this, now we are in a position to just solve one non-trivial problem, which I will try to do it. Look here. Are you able to see? Is there any problem? Hello on the.
No, sir.
All right. So this is the differential equation ut plus ux equal to 0 and u at t equal to 0, which is your u naught of x. This is given by 1 when x is less than or equal to 0. There is no need of defining this on the front as a matter of fact. 1 minus x by a, 0 less than a, and this is 0 when x is greater than a. This is your initial value problem, assuming that the evolution of u in 1, this is your partial differential equation, this is your initial data, assuming that the evolution of u in 1 is governed by this conservation law. That is very important, right? There is a need to specify the conservation law. By the conservation law, this is the conservation law. So how to look for the solution now? Can you, now you have to tell me that how to proceed. How to proceed. What is the initial profile? This is your initial profile. This is axis of x. This is your u naught x. On the left, it is 1, so a constant state. Here, u naught x is your 1 on the left of x is equal to 0. On the right, this is u naught x is your 1 minus x by a. When x is equal to a is some number, constant, which is positive. So look here, when a is right, when x is equal to a, this is 0, and here u naught is 0. This is your initial profile. Is that right? Hello?
Yes, sir.
Okay. So now how to construct the solution? Please help me. How to construct the solution in the xt plane? How you will start? Hello? Somebody should guide me that how to proceed further, so that I am sure that you people have fully followed whatever I have said during these 6 lectures. Hello? At t equal to 0 on the left, u naught x is equal to 1. Is that right? On the right, this is your point A, and beyond this, on this part, of course, u is specified by this. So if psi is any point here typical, u naught psi will be your 1 minus psi by a, right? Here if psi is any typical point, so u naught psi will be 1. Here if psi is any typical point, here u naught x. Tell me what is u naught x here? When x is greater than a, it is 0.
0.
0. Very good.
0.
0. Correct. So now how to proceed now? We have to look for the characteristics issuing from this part of the real line. Am I right?
Yes, sir.
So what are the characteristics issuing from this part of the real line? Characteristics issuing from various points, right? Xi less than 0. So what do we get? These are the analytical form, you know, that x is equal to xi plus t times u naught xi, and along these characteristics, u is equal to u naught of xi. This is the analytical form of the solution. So here u naught x is 1. So if xi is any typical point, at that point u naught xi will be 1. So what are the characteristics? The characteristics are
Xi
plus
plus t.
psi plus t, and therefore here psi is equal to 0. So this is the leading characteristic of this family. These other characteristics, they will be, yes, parallel to this. These are the characteristics originating from this part of the real line, and therefore what is the solution? The solution will be, tell me what is the solution here in this region?
X is equal to xi.
U is equal to
U equal
1.
to 1.
Because these characteristics will carry this information into the region. Each characteristic will take this u is equal to 1. So u is equal to 1, yeah, on the whole of it. Is it all right? Hello?
Yes, sir.
Oh, okay.
Sir, yes.
Now, what happens? What are the characteristics issuing from this part of the real line? Characteristics issuing from this part of the, from 0 to a, that is xi varies from 0 to a. I am concerned with this part. This part I have seen that these are the characteristics and they carry this information. Tell me quickly, what are the characteristics issuing from this part of the real line 0 to a? What are the, tell me the equations. Hello? Characteristic issuing from any point on this line would be what?
So x equal to xi plus
Okay.
t into 1 minus xi by a.
So characteristic would be what? X is equal to xi plus t times what? What do you say?
1 minus xi by a.
Excellent. Very good. Wonderful. Wonderful, Professor. Wonderful. X is equal to, so these are the characteristics showing from this part of the real line, 0 to a. It follows from here quickly. X equal to xi plus t times u naught xi, and u naught xi is given by this expression. Therefore, these are the characteristics. Now I have to find the solution. So what is to be done? This I have said n number of times. If we can solve this equation for xi, it is an implicit form, right? If I can solve for this xi, plug that value of xi here and you get the solution, u as a function of x and t.
Okay, sir.
So what is to be, so this implies that you have to solve this for xi. So xi into 1 minus t by a, am I right? Hello? Xi into 1 minus t by a plus t, am I right? Hello?
Yes, sir.
Yes,
Yes,
sir.
sir.
So this implies that x minus t, am I right?
Yes, sir.
Upon a minus t, I will write now. This is your xi by a. Is it correct? Please check this calculation. Is it right?
Yes, sir.
Very good. And if I, so what is my objective? My objective is to get rid of this xi. Substitute this xi as a function of x and t here. What is u is equal to u naught of xi? I know that u is equal to u naught of xi is given by this relation. Is that right? Hello?
Yes, sir.
Yes, sir.
So u of which is a function of x and t is your u naught 1 minus xi by a. Xi by a I have calculated. X minus t upon x minus a. So what do we get? Please simplify it.
Yeah.
X cancels with minus x. So what do we get? T minus a. Please check this calculation. Is it correct?
Sir, yes.
Is it all right?
Yes,
Hello?
yes, sir.
Is it right?
Yes, sir. Yes, sir.
Okay. It means what? By the way, what is the characteristic issuing from this point x is equal to a? Can you tell me?
X equal to xi.
x is equal to a. So x.
Sorry, x equal to.
Yes. So what is the characteristic is showing from this point? Or I will say that xi greater than a. All right. Xi greater than a. So you are very right.
X
That
equal to xi.
equal to xi, wonderful. X is equal to xi. All these characteristics they originate from here, and they will take which value of u? Hello.
U is 0.
Excuse me, sir.
Very good. U is equal to 0. So in this part, U is equal to 0. What happens at this point where they intersect? What are the coordinates of this point? Can you tell me? Here, this is the line x is equal to a, and this is the line x is equal to t. Am I right?
Yes, sir.
Where do they intersect? Obviously, the x coordinate has to be a,
Yes.
right? And t coordinate is also a. Is that right? Hello?
Yes, sir.
A. These are the coordinates of this point. Let me call this point as P. So look here, the scenario is somewhat like this because all these characteristics, they will. So now what will happen to these characteristics? We have seen that these are the characteristics. These are the characteristics, right? X is equal to xi plus t times u naught xi, which we wrote like this and which we wrote like this. Can you tell me that what happens at x is equal to, this is the point, x is equal to a, am I right? T is equal to a. What happens at t is equal to a and x is equal to a? Can you tell me? This solution becomes overdetermined at this point, on this line. This is the line t is equal to a, am I right? Hello?
Yes, sir.
Yes, sir.
So solution is overdetermined at this point P, at A. Because it's very clear here the solution, what will happen to the characteristics? All these characteristics which emanate from here, they will converge at this point, You can see here, if look here, when x is equal to, as a matter of fact, as I said, at the point AA, if you just before AA, what happens? You can see here that all these characteristics, in fact, they are merging at this point AA. Is that right? Hello? These are the characteristics. Okay? Is it all right? Hello?
Yes, sir.
Sir.
So all these are your simple straight lines. All these straight lines,
Meeting at the same point.
simple coordinate geometry. All these lines, they are meeting. It means what? This characteristic will carry this information, which is different from this information, which is so different characteristics. They take different values from this part of the real line, and here they right. The solution becomes indeterminate. Is that right?
Yes, sir.
So at x is equal to a, t is equal to a, the solution becomes indeterminate. But then you see what will happen. This characteristic is like this, and this characteristic goes like this. Beyond this, so here it is here you see all these characteristics intersect. So there is but before this, what happens? So we can write the solution. Solution in the region. This, that is, or I would say that interval, solution in the interval. In the interval, t, which is greater than or equal to 0, is less than a. What is the solution? The solution I can write uxt. This is on the left, it is 1. On the, this I can write that this is the line. Here the line x is equal to t, and x is less than t. And in this interval, this is your x is equal to t, and this is your x is equal to a, right? Here you use this expression, that is t minus a divided by x minus a. Is that right? T, x is greater than
X minus a
Excuse
by
me,
t
sir.
minus a. X minus a by t minus a.
Pardon, what do you say?
So it should be
X minus a by t minus a.
U is your 1 minus x minus.
Yes, it's okay, sir. We have to subtract it from 1.
Yes, subtract. This is the final result.
Yeah, yes, sir.
So t minus a upon x minus a, and when t is greater than a, the solution is 0. Is that right?
Yes, sir.
Yes, sir.
So this is the solution in this time interval. Is that right?
Yes, sir.
So the solution consists of two distinct time intervals. Now you look here, this is a singular point. So a discontinuity has to be fitted at this point. Hello?
Yes, sir.
A discontinuity, according to that theory, if the characteristics intersect, in order to extend the validity of the solution beyond this breaking time, it is necessary to introduce a discontinuity originating from this point. So what is the discontinuity? So I will write, in order to extend the validity of the solution.
Sir, please scroll up your screen.
Sure.
Okay, thank you.
Of the solution beyond breaking time, that is t is equal to a. Yes, we need to introduce a discontinuity, and that discontinuity must satisfy. Hello, the discontinuity must satisfy the RH condition. Is that right? The discontinuity must satisfy the RH condition. So what is the RH condition? RH condition is dx dt is f of ul minus f of ur divided by ul minus ur. Is that right?
Yes,
The
sir.
discontinuity has to satisfy this. And this is again ul plus ur, because I don't want to repeat the calculation. It is your half of, now what is ul and what is ur? Can you tell me? Look here. On the left of this discontinuity, if you look here, a discontinuity has to be fitted into this region. On the left of this discontinuity, what is u? U is 1. Right? All these characteristics, they will carry this information. These characteristics will go further because they don't intersect. Is that right? They don't intersect. These characteristics, they are not intersecting. Is that right? Eventually, they will intersect this line x is equal to a. And here we are going to introduce a discontinuity. That is right here also. These characteristics, they extend. Right? They are going to meet this line. Correct? And here in this region, the solution is multi-value. So we want to introduce a discontinuity here, and this discontinuity should satisfy, yes, this is your 1 by, so this implies what? X is equal to t by 2 plus some constant. Am I right? How this constant is to be evaluated? Because it originates from AA. Hello? This discontinuity originates from the point AA. Is that right? Hello?
Yes, sir.
When x is equal to a, t is equal to a, the constant is a by 2. Am I right?
Yes, sir.
So x is equal to a plus t divided by 2. This is the discontinuity. This is the discontinuity. This is the discontinuity which satisfies the RH condition as okay, as well as the stability criterion. Does it satisfy the stability criterion? I am introducing a discontinuity. Hello?
Yes, sir.
Does it satisfy a stability criterion? What is the speed on the left? The speed on the left is u is equal to, these characteristics, they will carry this value u is equal to 1. So on the left u is equal to 1, on the right u is equal to 0. Is that right?
Yes, sir.
So the characteristic speed satisfies this requirement. You see, so a discontinuity which satisfies RH condition and which satisfies this stability criterion is referred to as a shock wave. Have you heard of this term shock wave, by the way?
Yes, sir.
Actually, I think the wave has, this name has been given, but it's a shock solution. It is the solution, right? It's a discontinuous solution. The name of the discontinuity, I told you, wave means solution. Solutions represent a wave. and such shock solutions. So what is shock? It is a solution. What is shock wave? It is a weak solution of a hyperbolic conservation law. Is that right? What is shock wave? It is a weak solution of the hyperbolic conservation law. We have just seen the characteristic speed on the left is greater than the characteristic speed on the right, and the speed of the shock has to be intermediate between these two speeds, correct? So when both these conditions are satisfied, RH condition is satisfied and this stability criterion is satisfied, a discontinuity has to be fitted. So look here, the solution, this is the solution at this point AA, this is right, and beyond this, the discontinuity from this point onward, the discontinuity is x is equal to a plus t by 2. On the left, u is equal to 1. On the right, u is equal to 0 all through. U is equal to 1, u is equal to 0. So you can see here that the second solution greater than a. So the complete solution consists of two distinct intervals. One is this interval 0 to a, in which I have already mentioned that this is the solution. The other one would be, that is for t greater than a, the solution would be what? 1 when x is less than a plus t by 2, and 0 when x is greater than t. Now you can see that it is, please verify that it satisfies the stability criterion, right? It satisfies the differential equation identically. Please verify it satisfies the differential equation identically, satisfies the initial conditions. Now, very interesting, if a goes to 0 in the limit, just see that it gives us the result example 2 which we have discussed. In the limit, when a goes to 0, we recover the result of example 2. Okay, so the time is up. I don't want to take any other's time. Please tell me if there is any difficulty.
Excuse me, sir.
Yes.
So while defining u, x, comma, t in this page, yellow colored,
Yes.
you have taken one u naught xi is equal to 1 minus xi by a. But earlier you have introduced xi by a is equal to x minus t upon a minus t. So when we replace xi by a by x minus t upon a by t, the value of u, x, comma, t should be different, I think.
Oh, why? X are simple, Baba. X minus a minus x. X gets cancelled. Plus t.
Sir, you have taken 1 minus x minus t upon, it should be a minus t, I think.
अरे भाई, इसका एल्शियम क्या आएगा? X minus a.
Sir, please scroll it.
तो यहाँ क्या आएगा? X minus a. Am I right? Hello?
Sir,
Sir,
in
please
denominator
scroll
it
it.
is a minus t.
X plus t. X cancel हो गया. So
Sir, in the denominator, it should be a minus t, I think. You have defined xi by a.
Of this, you have taken x minus a.
oh, xi by a is x minus a minus t. Am I right? Hello?
Yes.
Yes. Yeah, very good. X minus
This
t.
is the way, a minus t.
Please make this correction. Please make this correction. Very good. Very nice. Thank you. Thank you very much.
A minus t.
Yeah, very good. So what is the numerator now? Tell me quickly. A minus
t minus x plus t.
Gets
A
cancelled.
minus x over a minus t.
Very good. So your solution turns out to be
x minus over x minus t.
x. What is that? A minus t minus x plus t.
Yes,
So t
A minus
cancelled
x over
a
a
minus x.
Finally, final output is same.
Divided by a minus t. All
Yes.
right. All right. But our discussion remains in very
Remains same, yes sir. That is
Yes, sir.
all conclusions are same.
all conclusions. Very good. Very nice. So thank you very much. Now, if there is any other query, I would be
Any
very.
other questions from participants?
Yes. Yes.
Sir.
No.